So yeah, my name's Moiya McTier. I'm a grad student at Columbia. I'm getting my PhD soon, and I'm going to tell you about work that I did with my two advisors, Keith Hawkins, who's now...
He was just here.
Really? Mm-hmm. Oh, Keith's great. Yeah, he's at Texas now, and Catherine Johnson, who is still at Columbia. She's going to be there for a while. There's a lot of stuff that we actually can't observe in our own Milky Way galaxy, and so I'll give you a few examples. One, how long is the galactic bar that's at the center of our galaxy? So that's this bright kind of box of stuff that you can see at the center of our galaxy. We have no idea how long it is. We have an idea. We don't know for sure. We know that it rotates, but we don't know how quickly it rotates. We don't know how quickly the spiral arms of our galaxy rotate, and that's kind of a big problem because the bar and the spiral arms are characteristic features of our galaxy. When you think of the Milky Way, this is probably what you picture. You picture the bar and the spiral arms, but we don't know everything about them. So that's kind of embarrassing, actually, as an astronomer. And we also don't know what the gravitational potential profile of our Milky Way is. So we don't really know how much mass there is in different parts of the galaxy and how that affects gravity overall. So this is a problem. We want to know these things, but we can't observe them in our own galaxy. Does anyone know why? Why is it hard to observe these things in the Milky Way?
The dust.
Dust? Yeah.
Well, we're in the Milky Way. We're inside it.
Exactly, yeah. We're inside the Milky Way, and observing the Milky Way from inside it is kind of like trying to see your own face without a mirror. It's impossible. So we have to actually study all of these things indirectly, and astronomers have come up with really creative ways to indirectly study these things. Yeah.
Do we actually know how many stars are in a galaxy?
No.
Because I hear 100 billion, I hear 200 billion. I've never heard a number.
Right, yeah, we have best guesses based on...
What's the current best guess?
Between 10 and 100 billion.
Oh, come on.
Right. But to an astronomer, that's within an order of magnitude, so that's a good guess, right?
But 10 billion doesn't sound like very many.
No, but it all depends on how massive we think stars should be, because we have an idea of how massive the galaxy is, and then how much dust.
I always thought that it took us, the Earth, our solar system, to go around the whole galaxy 250 million years.
Mm-hmm.
Does that give us an idea how big the galaxy is?
It gives us an idea of how much mass is inside
our orbit.
Yeah.
But not outside.
Not outside. We have an idea based on looking at other galaxies orbiting the Milky Way. We have an idea of how massive the Milky Way is. But it's hard to turn that mass into a number of stars unless you know how many stars of what mass there are.
Is 100,000 light year diameter still a good number?
Oh, I'm thinking light years. I guess about like 30 kiloparsecs is the unit I think in. I can't do the conversion.
It's 3 point something, 2 something.
Yeah, so it's in that ballpark.
In that, yes.
Oh my God.
All right. Do you have a question?
How did the Milky Way get made? Because is there any? Because it's like really pretty, but we don't know how it got made. And it's the shape of a spiral. But if there's stars in it, how did the stars transform to make it into the Milky Way?
That's a really great question. The best guesses that we have are that there was a little bit of mass, probably dust and gas, and then because it had mass, it pulled other dust and gas towards it. And when dust and gas collide, when gas collides, you make stars. So that's how the stars got made in the Milky Way. Okay, I'm gonna move on. So talking about moving groups, which is how we indirectly study the things that I told you about on the last slide. So moving groups isn't a new field. We've been studying moving groups. I haven't. Astronomers have been studying moving groups since the 60s. And moving groups are groups of stars that are moving at similar speeds and in similar directions. So they're clustered in what we call velocity space, even though they don't necessarily have to be anywhere physically near each other in the sky. So they can be in different parts of the galaxy, but because they're moving in the same way, we call them moving groups. Does that make sense?
Yeah.
Thank you. So the idea behind using moving groups to indirectly study the Milky Way is that we know where these stars are now, and we know how they're moving. And if we know those two things, that means we can work backwards to figure out where those stars started. And once we know where stars started, and we know where they were all along the way to where they got now, that tells us how the galaxy has changed over time, which is what we're really interested in. And the only reason we can do that is because we know how moving groups form. They form in 3 different ways. One is by pulling matter in from the galactic halo. So there's the Milky Way galaxy, which most people think of as like a thin kind of pancake with those beautiful spiral arms. But that's not all there is. There's also a galactic halo made up of dark matter and other kind of smaller satellite galaxies that orbit the Milky Way. And so there's a lot of matter that can be pulled in to the Milky Way because of gravity. And when that matter gets pulled in, it gets elongated into these really long streams that are all moving, in the same direction and at similar speeds, which is the definition of a moving group. So that's one way that moving groups can form. The second is by breaking apart clusters of stars. And this happens because the stars closer to the center of the galaxy will be moving much faster than the stars further away from the center of a galaxy. Even in a star cluster, that's how there can be a big enough difference in their velocities, even within one cluster. So over time, yeah.
So it's sort of like a solid body disintegrating when it passes the Roche limit, but because it's the forces holding the cluster together are not as strong as the difference in forces of the because they're at a different distance.
Exactly. And so over time, over many orbits, the stars will start to separate, and you again get these long streams of stars that are moving in similar speeds and similar directions, and that's another way to form a moving group. The third is my favorite because this is the way that we can actually start to study the bar and spiral arms, and that's by individual stellar orbits existing in resonance with the motion of the bar or the spiral arms. So this, yeah.
How can't we see the stars moving, but in outer space they move, but when we're looking in the telescope it doesn't look like they're really actually moving?
That's because we're not looking for long enough periods of time. And also, stars that are really far away, it's harder to see when they move. Have you ever been moving in a car and you look out the window and the stuff that's closest?
Yeah, when I was in the car, I saw some planets. Yeah, but they're actually kind of like moving around in a circle around the orbit. But you just can't see them. But why are they white if we look at them? They're like always white. They don't. And then when we look in the telescope, they have colors, and on the outside they look like white stars.
You do realize you just answered the first question on your own.
Exactly. Maybe we can talk about that after, because you're asking really great questions. Okay, I'm gonna keep talking about resonances. So the idea behind this is basically that as a star is moving around, if it's in resonance with the bar or the spiral arms, then at the same point in that star's orbit, it gets pushed by the bar, or pulled, pushed or pulled. And so you can think of this as, like the dad in the background is the galactic bar, and the kid on the swing is a star. And so at the same point, that star is getting pushed, and over time that will create over and under densities, so there will be more stars in one place and fewer stars in another place, and that is how you can create moving groups. All good? Any questions about these mechanisms? Great. All right, so after I did the background research and I learned that these are the different ways that you can form moving groups, my research goal was pretty clear. I wanted to identify moving groups because we've gotten some new exciting data this year, and so I can use that new data, better data than we've had before, to identify new moving groups. And then I want to use the chemistry of those moving groups to actually figure out where they came from, how they formed. And I like to think of myself as a kind of forensic scientist, but in the galactic sense. So are any of you into like CSI shows or anything? Show of hands. Okay. So you know how in those shows forensic scientists can study like stomach contents or something to figure out where someone has been before a crime was committed? That's kind of what I'm doing with the galaxy. I'm studying its organs, these moving groups, and I'm figuring out the contents of those organs to figure out, to find where they came from.
What about a globular cluster? Is that a gigantic moving group?
It can be. I mean, the two can overlap, but it's unlikely that all of the stars in that globular cluster would have the same velocities.
Oh, really?
It would depend on how big it is. It really depends on a lot of different things about like how that globular cluster formed. Which is why we like to think in terms of moving groups and not clusters of stars, because moving groups pays attention to how the stars are moving, which makes it easy to trace back their orbits over time to the beginning, like to the formation of the galaxy, or at least the formation of those stars.
But do we even know how globular clusters got formed?
I don't know.
Well, if you don't, I don't either.
So we don't.
Yeah, we don't.
Maybe people.
Maybe
in the
everybody
world
else
do.
knows.
Yes.
No one.
Great. So this is my research goal. To achieve this goal, I have to use data, and I'm using two different data sets. The first data set is from the Gaia spacecraft. Have you heard of Gaia?
Mm-hmm.
I'd be surprised if a group of people who love astronomy hadn't heard of Gaia, because astronomers were super excited about it all year. Gaia is really amazing because it's given us really precise positions and motions for over 1 billion stars in the galaxy. And I have a figure later where I actually show you the positions of all of those stars, and it's really amazing how far out it goes, how far out this survey has gone. It's what we call an Astrometrics Survey, which is just astronomers speak for saying, this survey is telling us the positions of stars. So it told us about over 1 billion stars. 7 million of those stars have radial velocity measurements, which is really exciting because when I have the positions and the motions of stars and their radial velocities, then I can calculate their velocities around the entire galaxy. And I also use those pieces of data to calculate to calculate what astronomers call action coordinates. And that's a way of describing a star's orbit around the galaxy, but I'll get more into that later. So that's one data set that I use. The second data set that I use is called GALA. And because astronomers are really great at acronyms, GALA stands for Galactic Archaeology with Hermes. We get really creative with what letters we choose to use in the acronym. But GALA is a spectroscopic survey of the southern sky. So it's actually a ground-based survey. The telescope that this instrument is on is in Australia. And it has observed over 300,000 stars. And for all of those stars, it has measured chemical abundances from 23 chemical species. So 23 different elements, which is a lot. It's a lot of data, which is really what took most of the time in this project, just digging through all of that data and figuring out how to deal with so many data points. So this is to show you where those stars actually are. This is the subset of all of those Gaia stars that have radial velocities. I didn't even bother to show you all of the Gaia stars because it would have kind of crashed my computer. The file would have been too big. But this is just the subset with radial velocities. The yellow star is where the sun is, and going towards the right of the plot is moving towards the center of the galaxy. So it gets pretty far. It actually extends to the other side of the center of the galaxy. And then, so this is the data set that I started with. And now I'm about to show you the data selection process. So I'm going to take you through all of the cuts that I used. I wanted to get rid of all of the stars that had high error bars on all of the velocities. So I went from about 7 million to almost 5 million, just by getting rid of stars with high error bars on their velocities that I calculated.
And these are just on the radial velocities or on the proper motion?
On the velocities around the galaxy, not
Okay,
just
the
the
full
radial.
vector.
Yeah, full vector velocities.
I'm sorry, I just had one other question. So
Yeah.
Gaia measured proper motion as well as radial velocity over what time period?
Over, with the second data release, 4 years.
Okay, so they're basing their proper motions on 4 years of motion.
Mhm.
Okay, thanks.
Yeah, in the first data release, which came out in 2016, I think, they didn't have a very long baseline, so they actually combined with a different survey called Tycho.
Okay, got it.
All right, so this was my quality cut, where I got rid of stuff that had bad data. Next, I make a distance cut, because I'm only interested in the stars that are really close to the sun, because I want to find moving groups that are in what we call the solar neighborhood. So these are all of the stars that are within 600 parsecs, and to put that in light years, I think it'd be 1,800, 1,900 light years. And so that's all of the Gaia stars that I have. When I identify the moving groups, I do it with this subset of stars, so almost 2 million stars, which takes a really long time. It's super computationally expensive. Next, I'm going to show you all of the stars that have chemistry, and this is going to feel like a kind of extreme cut. So I go from 2 million to 37,000. So only 37,000 of my Gaia stars have Gaia data, which seems kind of small, but it's more than anything that people have worked with in the past. In the past, people have done these types of studies with maybe 5,000 stars, so this is a huge improvement. Any questions on the data cuts?
I'm assuming the upper left is missing because Southern Observatory.
Exactly, yeah. One of the ways that I could improve this, one of the ways that I could improve this study is by combining it with a northern spectroscopic survey, but then I'd have to worry about how are those two surveys systematically different. Basically what I have to do is wait until the Gaia survey switches to a different telescope and observes in the north. That's all I can do. All right, so now I've told you about the data that I used. I want to tell you about the actual research that I did, the analysis that I did. Historically, moving groups have been found in velocity space, and they're called moving groups. It's about how stars move. So this is the coordinates. These are the coordinates that I use in velocity space, where one of the vectors points away from the galactic center, one points towards the galactic north pole. I actually just ignore that vector because there's not much up and down motion around the sun. And then the other vector points in the direction of motion for the sun, so it actually moves, like it's a curved vector around the galactic center. And these are the moving groups that I found in velocity space.
Thank you.
I found 27 moving groups using a machine learning algorithm called Gaussian mixture models, and I would love to talk to you about Gaussian mixture models after this if you have time or interest, but I don't have time right now, so I'm gonna keep going without talking about Gaussian mixture models. But so these are the groups that I found in velocity space. This is historically how people have defined moving groups, but this year someone looked at this and thought, what if we didn't find groups in velocity space? What if we found them in action space? And so action space describes the star's entire orbit instead of just describing a snapshot of the star's motion, which is what velocity space does. And so this is actually a more accurate picture of how a star moves over time. And what I did was take all of the moving groups that I found in velocity space, and I just translated them over into action space. So this is what, this has actually been done before. A team led by Wilma Trick, who is an astronomer in Germany, did this earlier this year. And what she found, and I confirmed this, was that groups on opposite sides of velocity space will actually overlap in action space. And so I'll show you another example of that. Those are two groups on totally opposite sides, but they overlap in action space. And that makes sense because action space describes a star's entire orbit. And so two stars can have very similar orbits, but be in different parts of their orbit, almost like they're in different parts of their year. And so one star would be moving towards us and the other would be moving away from us, and that would put them on totally opposite sides of velocity space. So Wilma Trick saw this, and she said, astronomers, start using action space to talk about moving groups. And I was like, yes, Wilma Trick, that makes sense. But what if you also use chemistry? Because I have all of this chemistry data. So what I did was actually go back to those moving groups that overlapped in action space, and I said, what if we compared the chemistry of those moving groups? Because the way that we know that moving groups forms tells us that moving groups should be chemically similar. And my concern with what Will McTier found was that maybe some of these groups just happen to overlap in action space and aren't actually chemically similar. So I went through all of the overlapping groups and I compared their chemistry. And so I can actually do this with you by eye. These are just 2 examples, but I have a lot more. And so the one on the left, do you think those 2 groups have similar chemistry? Who says yes? Who says no? All right, okay. What about the group on the right? Do you think those 2 groups have similar chemistry? Who says yes? Who says no?
Yeah.
Okay, yeah. So the 2 groups on the right actually have very different chemistry, and this is just in iron, but I told you I have 23 elements. So they actually look very different in all of the other elements too. And that led me to the conclusion that sometimes groups will overlap in action space, but they'll actually be 2 distinct populations, and we need to study them as distinct populations. So I guess the message that I have for the astronomy community is that actions are more important than velocities. Will McTier was right. But chemistry is really important, almost more important than both. So if you're going to do this type of work, you need to start characterizing and defining moving groups based on their chemistry. And when I do that, this is the map of moving groups that I find, where sometimes the moving groups are on different sides of actions of velocity space, but they're actually the same group. And sometimes they're not. So this blue group and this green group, this blue group and these 2 red groups would have been considered the same by Will McTier, but when you go in with chemistry, you find out that they aren't. So now what? After I've done all my work, what can I do with it? Well, I can give all of my chemistry information, all of my chemically similar moving groups to other astronomers, and they can use those to trace back the evolutionary history of the Milky Way. And so I told you that I like to think of myself as a forensic scientist, but in the galactic sense. I like to think of other astronomers after this as the cops, because I'll give them my analysis of the contents of the organs that I found, and they'll actually go out and do the work of finding the bad guys and then arresting them. So that's what I can give to the community. And just to summarize, in case you dozed off at some point while I was talking, if you remember nothing else, I want you to remember that moving groups are groups of stars that move in similar directions and at similar speeds, even though they don't have to be near each other in the sky. I want you to remember that chemistry is really important, and it can help you separate 2 overlapping groups. It can keep you from making mistaken claims about which groups are actually the same. And third, astronomers can use these groups to indirectly study our galaxy's past so that we can learn about the galactic bar and its potential and the spiral arms, all of those things that we can't directly observe. Thank you for listening.
Can you tell how old these groups are? Does the chemistry tell you anything about age?
Yeah, chemistry correlates with age a little bit. Older stars
Have more iron?
Yeah, they'll have more heavy elements. There are a lot of different ways to study stars. Chemistry is one of them. If you did follow-up observations with these groups and you saw how the stars are rotating, that would be another way to figure out their age. Yeah.
Are we in a group?
That's a great question. Yeah, I'd say we are. So the sun is about here in that gray group. Yeah. It doesn't have a name.
Looks like somebody's abs.
I think if
The group on the top left, that's the one the sun is in?
So all of these gray circles are actually the same group, and the
sun's
sun
in those.
is in the middle of it.
Oh, okay. Makes sense.
Have you ever observed any object in the universe which has started changing over the period of time? Like there is no change happening anymore.
any object in the universe, I'd say brown dwarfs are pretty much dead stars. They're not changing much. They're very slowly cooling down. But no, most things in
We
space
call
are
them dead.
changing.
They were never alive to begin with.
Right.
Not really.
If you can think of stars as alive, stars as in they're actively fusing elements. They're undergoing their kind of life cycle. I guess astronomers think of this in terms of life cycle. So a brown dwarf would be the death of a star.
So, do we have prediction that it's never going to change in future?
That brown dwarfs will?
Yeah, like there will be no change in the state, no
No.
matter when we see it.
They're still cooling down.
There will be still some change.
Yeah, but it'll take so long that we won't ever see it. In fact, like the cooling time for a brown dwarf is longer than the age of the universe. So, essentially, they're not changing on any time scale that we care about.
Okay.
So because the chemical composition of the Milky Way, or at least these clusters, differs so radically, does that mean that at least the Milky Way did not develop uniformly at the same time? Or is there a difference between chemical composition as you moved away from the epicenter of the galaxy?
That's a good question. The galaxy didn't form all at once. It formed by pulling stuff in. And then there are different populations of stars. So there was a population of stars that were born near the beginning of near when the galaxy formed. And then they all went through their life cycle and died. And then new stars formed from that. And so there are a lot of different populations, or generations, I think. There are generations of stars. And so they are all chemically different. And in that way, the galaxy is very chemically different. But I didn't look at any pattern to see, as you move farther away from the center of the galaxy, does it get more chemically enriched or something?
Yeah, for like, do you see that the chemical composition is more elementary as you move outwards, or more complex as you move outwards?
What I would expect, I haven't studied this, what I would expect is that at the center of the galaxy, because there are more stars and there's just generally more activity, that there would be more elements, more heavy elements. And then as you move out from the center of the galaxy, there would be fewer heavier elements because stars aren't dying and being reborn as often.
Yeah.
And that's where stuff from the halo is coming in. And the halo, in all of the studies that people have done of it, has been shown to have relatively few heavy elements.
Oh, really?
Mm-hmm. The halo is typically characterized as low metallicity, which means there are few elements that are heavier than helium. Because to an astronomer, anything heavier than helium is a metal.
What about the bar? What's the do they even know why there is a bar? You know, why isn't the bar collapsed just to be encircled by the black hole?
It's because it's rotating. The
So
rotation of the bar
keeps it from.
Mm-hmm.
Is it rotating that fast that it allows it to keep that shape?
Yeah, the bar happens because of the way that stars' orbits will interact with each other, forms this bar-like shape. But we really don't know much about the bar. It wasn't until fairly recently that we knew it existed. So we're still learning a lot about it.
I had a question about the separation, the analysis that you did, breaking down the groups by chemistry.
Yeah.
I guess a concern I would have, and maybe it confuses your analysis, and maybe it doesn't. I apologize if it does.
Thank you. If it
That,
does.
stars of different masses will age at different rates and produce different chemistry. So even if they were all formed simultaneously, your heavier stars will now show a higher iron to hydrogen ratio than the smaller stars, right? So if you see diversity in chemistry, might you not be looking at diversity in mass?
We could, but most stars are low mass.
Okay.
So I think
Being
that
defined as what?
a
Half
few
the
solar
sun?
masses or less. Yeah, I mean, most of the stars in the galaxy, like 70% of the stars in the galaxy are M-type stars, which are less than half the mass of the sun. And so,
Okay, so that's what your average is working out fine.
Yeah.
Because it's not even the average, there's a big spike there, right, in the distribution.
Right.
So, okay, that answers that, thank you.
thank you. It made me do a little mental exercise. That was nice.
I tried to challenge you.
Is there a difference in the density of these groups? Like
Definitely.
one star every 2 light years, or one every 1 light year? Does that tell you anything where the density is much different?
So I'm only looking at a local volume. Remember, I'm only looking at stuff that's within about 2,000 light years. So the kind of spatial density is difficult to compare because everything's so packed together in physical space. But there are some groups that just have a lot more stars than others. This group down here, this big black group, has very few stars, and it has a very low metallicity, which tells me that it probably formed by coming from the halo, because the halo will just give us fewer stars because smaller galaxies are coming in from the halo. So yeah, some groups are more dense than others, I guess you could say.
How many stars are in groups? Like, what's like the largest and the smallest?
The largest and smallest that I have in my sample, I guess the largest has a little over 2,000 group stars that have chemistry. If I were just looking at how many stars it has in general, it would be hundreds of thousands, if not millions.
Wow.
Yeah.
What about like the
The
smallest one?
smallest has maybe like 20 stars that have chemistry, but I actually took those out. That's a good question, or it gets at a good point, which is that I wanted to have enough stars in each group with chemistry data to have reliable chemical analysis. So I'm not showing you any groups that had fewer than 50 stars with chemistry data.
Oh, okay.
And so your output here to the community is a set of what you believe is a consistent action group,
Mhm.
right?
Mhm.
Chemically consistent action.
Chemically consistent groups,
So-
and I will give it to them in both velocity and action
Of course,
space.
yeah,
Yeah.
but sort of labeled by, okay, these are together, these are
Yeah.
together.
On the left diagram, the coordinates are velocity
Mm-hmm.
in 2 axes.
Yeah.
So, like that bottom group, that covers a big area,
It does.
big range of velocity. So how do you make that a group?
Mhm. That kind of gets into how Gaussian mixture models work. So the way that they work is by, I actually have a
I'm sorry, are you saying galaxy mixture model
Gaussian.
or Gaussian?
Gaussian mixture model. So the way that Gaussian mixture models work is that it looks at a data set, and you can tell it how many Gaussian components you want it to fit. Basically, how many blobs do you want it to use to describe this data set. And then the algorithm goes in and it assumes that a model can be made with that many blobs, and it then compares that model to the observed data. In my case, it does that over 1 billion times, and then it gives you the most likely model of blobs. And so there is a downside to this model, to this algorithm, in that it assumes that every star belongs to a group, which isn't great. But it is really powerful in that it can find groups that are really spread apart, where other clustering algorithms would try and make groups really small. So that's
It's looking
why.
for a Gaussian distribution, like a shape, isn't it?
Yeah. Oh, where is it? So that's why this group can be really big. Other groups would probably split this up into a lot of small groups.
And so you predefined the, I know a little bit about, sadly, about Gaussian mixture models. You predefine how many
Mhm.
groups you're looking for?
Yeah, and to do that, I use another algorithm that tells me how complex the model should be.
Okay.
It's called a Bayesian.
Yep.
Great. Bayesian information criterion. For those of you who want to like go home and Google it or something. But that test will tell me how complex my model should be, and then I use that number when I'm running the Gaussian mixture model.
Did you say machine learning in the middle of all that?
Yeah.
So what about the application of the mixture model is driving you to use machine learning?
It's that the Gaussian mixture model itself is a machine learning algorithm. It's kind of unsupervised. So it's not like an MCMC where it's moving towards a more likely parameter space. The program is actually learning over time what blob placement is best. Anything else?
Wow.